Hello students, this is Dr. Anita Raj, your chemistry mentor, welcoming you for another session in the structural elucidation of glucose. In the previous session, we saw the open chain structure of glucose, and today we are going to see about the cyclic structure and the Haworth projection formula of glucose, right? See, the open chain structure of glucose, which we saw in the previous session, explains most of its properties. However, it is unable to explain the following reactions and the facts. Okay. So now we are going to see the cyclic structure of glucose, that too the evidences against the open chain structure. So first we shall see the evidences against the open chain structure, right? The first one is glucose does not give 2,4-DNP test, Schiff's test, and it doesn't form bisulfate addition compound. Okay. See, in spite of the presence of the aldehyde group, see, this is the normal open chain structure of glucose. Here we are having the aldehyde group. So, in spite of the presence of an aldehyde group, glucose does not give this 2,4-DNP test. Okay. What do you mean by 2,4-DNP test? Actually, 2,4-DNP stands for dinitrophenylhydrazone. Okay, and this 2,4-dinitrophenylhydrazone can be used for the qualitative identification of ketone or aldehyde function. Okay, say it's actually the hydrazine group which is present in this 2-nitro, that is dinitrophenylhydrazone, will be reacting with the aldehyde for the ketonic group, producing a positive test. Okay, see, if suppose if the positive result mean 2,4 DNP test means that your unknown will be containing either an aldehydic or a ketonic group. That means the glucose should contain a aldehydic or a ketonic group if this shows a positive test. Actually, this glucose is showing a negative result for this 2,4-DNP test. That shows that it is not having a free aldehydic group. Understood? The next one is the Schiff's test. What do you mean by Schiff's reagent? Actually, Chips reagent consists of a solution of fuchsin dye, okay, that has been decolorized by sulfur dioxide. It has a fuchsin dye that has been decolorized by sulfur dioxide and is used to test the aldehydic and the ketonic group. Okay, this is Schiff's test, right? And now, usually, if we are making use of an aliphatic aldehyde or a aliphatic aldehyde, it will be restoring the pink color instantly in the Chips test. Okay, but here, since as we are using glucose, this is not restoring the pink color. That shows that there is no free aldehydic group or ketonic group. Understood? And also it is not responding to the bisulfate addition product. Okay, addition compound. Mean it is not reacting with sodium bisulfite. Okay, it is not reacting NaHSO3. So it is not reacting with sodium bisulfite to form hydrogen sulfate addition product. So this is the first evidence that is no reaction with no positive reaction with DNP test, no reaction with STIPS test, and no reaction with bisulfite. Okay, so this is a very good evidence against the open chain structure. Okay, so the next evidence is the pentaacetate. Pentaacetate of glucose does not react with hydroxylamines. This indicates the absence of free CHO group. See here, pentaacetate. Yes, actually, this is the this is the open chain structure of glucose. When this is treated with acetic anhydride, we'll be have 5 molecules of acetic anhydride. We'll be getting pentaacetate. That shows the presence of OH group. Okay, 5 OH groups. Okay, that shows the presence of 5 OH groups. So, but what happens is this pentaacetate, after the formation of pentaacetate, this glucose does not react with hydroxylamine. It will not be reacting with hydroxylamine. This is a good proof that indicates the absence of the CHO group. Okay, there is absence of CHO group. Next, why there is no free CHO group? Why this group is not present in glucose free CHO group? This is because glucose forms hemiacetal between the CHO group and the OH group of C5. Which is C5? This is C5. So this OH group will be reacting with the CHO group and it forms a hemiacetal. It forms a hemiacetal. Okay. So during the formation of hemiacetal, the CHO group interacts with the OH group of C5, that is the fifth carbon. Okay, resulting in the formation of a six-membered ring. Okay, this will make the first carbon an asymmetric. See here, This is one group, this is another group, and this is attached to another group. Okay, and now this is attached to O. So this is an asymmetric carbon. So this makes this hemiacetal form makes the C1 carbon an asymmetric carbon. Okay, it makes a asymmetric carbon, and thus two possible arrangements of H and OH around it is possible. So two possible arrangements are possible. See here, this is one arrangement and this is another arrangement. See here, the changes, we could see the change only in the HOH configuration. Can you see? Here the OH group is on the right side and here the OH group is on the left side. Okay. Thus, two stereoisomers are obtained. Thus, two stereoisomers are obtained. Okay. And they are named as alpha D glucose and beta D glucose. They are named as alpha D glucose and next one is beta D glucose. The two stereoisomeric forms of glucose differ only in the configuration of C1, that is hemiacetal carbon. Okay, such a pair of stereoisomers which differ only in the configuration around C1 are called as anomers. Okay, so these are different. We could differentiate only in the C1 carbon. Okay, only a difference is there. All the other things are the same. See, look, everything the same. Only this carbon is changing. That too in the configuration. Okay. So such a pair of stereoisomers which differ in configuration around the C1 are called anomers, and the C1 carbon atom is called as the anomeric carbon or the glycosidic carbon. Can you understand? What's the name of that carbon? Anomeric. Anomeric carbon. Which carbon is called as anomeric carbon? C1. Okay, C1 carbon is called as anomeric carbon or glycosidic carbon. Glycosidic. Understood? Glycosidic carbon. Okay. Right. The cyclic structure of glucose explains the absence of free CHO group and also the existence of glucose in two forms. These two cyclic forms will be existing in equilibrium with the open chain structure in aqueous solution alone. Only in aqueous medium, these two structures, stereoisomers, will be in equilibrium, okay, with the open chain. Can you understand? So I am summarizing, say it exists in two different crystalline forms, that is alpha D glucose and beta D glucose. The two cyclic hemiacetal forms of glucose or isomers differ only in the configuration of the hydroxyl group at C1 called anomers. Is it not? Only this is alpha D glucose, this is beta D glucose, this is the open chain structure. See here in the open chain structure we are having a free CHO group, whereas here in the cyclic structure we are not having. Is it not? There's a hemiacetal form. So we couldn't see the free CHO group. Okay, instead the CHO group has reacted with the OH group of C5 and hemiacetal form is formed, and this is the anomeric carbon where there's a change only in the configuration, that is OH group here is present on the right hand side, whereas here it's on the left hand side. Okay, see the ring structure of glucose has no free CHO group. That's correct, is it not? These two ring structures, they don't have any free CHO group, but it reacts with HCN and NH2OH. But these two react with HCN and NH2OH because these are strongly carbonyl reagents and are able to open the ring to form the aldehyde. Can you understand? So they are the strongly carbonyl group. They are strongly carbonyl group and are able to open the ring to form the aldehyde group. So this ring structure of glucose there is no free CHO group. Though it's not having free CHO, but it reacts with HCN and NH2OH. Can you understand? Next, we are going to see the very important one, that is the Haworth projection formula for glucose, that is Pyranose structure. What do you mean by Pyranose? Actually, this Pyranose is a six-membered heterocyclic ring with an oxygen atom, okay, and six carbon atoms. It has this Pyranose. This Pyranose has an oxygen atom and six carbon atoms, and it is a heterocyclic compound, okay. And it is present, actually this Pyranose is present in the cyclic structure of alpha beta glucose, okay, alpha beta D glucose. So since this Pyranose is present in the cyclic structure of alpha beta D glucose, we are going for this Pyranose structure of glucose, okay, that is Haworth projection formula for glucose. Let us see here. So the two forms of D glucose are shown by Haworth projection formula, that is Pyranose structure. See, this is the alpha D glucose and this is beta D glucose, and this is the Haworth projection formula, that is the Pyranose structure. So this is the Pyranose structure. See, in this Pyranose structure, you can see that all the groups on the right hand side in fixture projection. Those groups which are present on the right hand side. See here the group which are present in the right hand side. See here in C1, OH is present on the right hand side. So the group which is present on the right hand side will be directed below the plane of the ring. See here this is carbon, C1 carbon. This is C1 carbon. The group which is present on the right hand side is directed below the plane. And next check C2. OH is present on the right hand side. C2, OH is present on, it's directed below the plane. Can you understand? And those which are seen on the left hand side is directed above the plane. Okay. See here in C1, H is above, on the left hand side, and here in C1, H is above the plane. C2, H is on the left hand side, it's above the plane. OH, C3, OH is on the left hand side. See here, it's above the plane. Can you understand? So all the groups that are on the right hand side in the directed below the plane of the ring, and those on the left hand side, it's seen above the plane. So the terminal CH2OH, final one, that is here in the sixth carbon we'll be having CH2OH. Okay, so in the final terminal CH2OH groups lies above the plane of the ring. So it's above the plane. Here we'll be having one. Okay, CH2OH. And actually it's not shown CH2OH, right? So that's a seen above the plane. Can you understand? So the terminal CH2OH group lies above the plane. Can you understand? So now this is the Haworth projection formula for glucose. Now this alpha D glucose here we have, this is alpha D glucose and this is beta D glucose. Actually this alpha D glucose is obtained by crystallization of concentrated solution of glucose at 303 Kelvin. Alpha D glucose is obtained by the crystallization of concentrated solution of glucose at 303 Kelvin, and this melts, that is alpha D glucose melts at 419 Kelvin. Beta D glucose is obtained by the crystallization of hot saturated solution of glucose at 371 Kelvin, and this melts at 423 Kelvin. So these are the two differences we could see in the preparation and the properties, whereas the major difference is only in the configuration of C1. Okay. Well, fine students, I hope you might have understood what I have taught today. Let me meet you with another important topic in my next session. Until then, it's Dr. Anita, Geochemistry mentor signing off from you. Thanks for watching.